Hello and welcome back to Mr. Viola's physics classroom. Today our topics are distance and displacement and speed and velocity. So in most of your classes we've been doing stuff with all four of these things. Some of you are a little ahead of others, but we're going to give a little bit of a review for everybody so that you can keep them all straight and make sure we use the right vocabulary when we're talking about certain things. So the first thing we talked about was distance. We did a couple labs, the treasure map lab. We had a distance and displacement lab. Distance, you can think of total amount traveled. So how far did I go? Doesn't matter what direction. It's just strictly a magnitude measurement. So this is what's called a scalar. So distance, being a scalar, that means it only has a magnitude and no direction. Displacement is basically distance with a direction. When you include a direction with a magnitude, the word for that is a vector. So distance is a scalar quantity, displacement's a vector quantity. Vectors have direction. With speed and velocity, we know that speed is how fast something is moving. Velocity is similar, how fast plus a direction. So in this case, speed is our scalar quantity, and velocity is our vector. Again, vectors include direction. And so what we talked about in class is that when I have a vector quantity, again, it includes direction, I need to include that direction somehow in whatever I'm writing. So if I have a displacement or a velocity, vectors can be negative. Having a negative vector doesn't mean I'm walking backwards or that I am going down necessarily. It just means that I'm headed in a negative direction. So it may be helpful to start all of any problem you have or all of your examples by laying out what that direction is going to look like. The easiest way to do that is to take a coordinate plane and simply remind yourself of the direction that you want to have. So what I've just drawn says that anything headed up or to the right is a positive, left or down is a negative. And that will keep you straight. The important part is that opposite directions have opposite signs. So if I walk forward and then I walk backwards and I want to find a displacement, I need to subtract those two values. So once we keep our vectors and our scalars straight, we then moved on and we talked about what happens when we move. And so velocity and speed. And the difference between them is somewhat small, but can make a big difference. When we talk about speed, it's distance divided by time. When we talk about velocity, it's displacement divided by time. When I have these two, the difference is obviously in the top with distance and displacement. So when you're in your car, if you drive around the track is 400 meters around. If it takes you 1 minute, you would have a velocity of 400 meters per minute. If I do the same drive in my car around the track, and I want to find my velocity, you would need to look at your displacement. Even though you drove a distance of 400 meters, you have a displacement of 0 because you began your race and you finished your race in the same spot. So you would have a velocity or an average velocity throughout your trip of 0 meters per minute. That's really the big difference between speed and velocity. we have to take direction into account when we measure velocity. So the big takeaway, or the thing you all should have written down, were two equations. Speed is distance over time, and velocity was change in position over time. Box them in for you. Those were our two big ones. We're going to focus mostly on velocity. Those of you that have already done the common assessment, you've done this a little bit with the buggy cars. So the next step that most of you have taken at this point is to look at what these mean graphically. So if I have a position and time graph, there are several ways that you could have something drawn on here, several examples that all mean something different but are all very common to see on a graph like this. The first one would be if I had something similar to this. Just a straight line on a position versus time graph. I'm going to call it line 1. So this first line, this would indicate no movement. Nothing is moving. You're at a certain spot, a certain displacement, a certain position, and time goes by and nothing happens. You don't change your position at all. So you have no velocity. If I look at another example, perhaps something like this, and I called this line 2, this would indicate that I am traveling at a constant rate over time. So this is a constant positive velocity. And now the question could be asked, why is it positive? Well, for those of you that have already done this, you know that to find the velocity, I'm looking at the slope. So the slope of the line is my velocity. On any position versus time graph, the slope of the line gives you velocity. Well, the slope of this line is a positive number. When I do my rise over my run, I get a positive. So that means I have a positive velocity. If I have the exact opposite line, and I go down, so we'll call this line 3, this is still a constant velocity, but in this case it's a constant negative velocity. When I find the slope of this line, the rise over run, the rise portion of my slope will be negative because I'm actually going down and over. So I would get a negative value there, and so I would end up with a negative slope and a negative velocity. The final one, and we haven't really talked about this yet, but the final common way of seeing this is if I saw something that was curved. Now curved is a little bit rarer. As you can see, it's no longer a constant slope. My slope is changing throughout. So what this means is that I am speeding up. I still can find my velocity by getting the slope. It's just that every slope is different, and so I eventually can figure out how much I'm speeding up by based on the difference of the slopes as I go up. So this is one that we're going to save for later, but these other ones are ones that you've seen quite a bit already, or you will see quite a bit coming up. For some of you, we've gone past this point. So if I move past this, and I start looking at other types of graphs. We've looked at velocity versus time graphs, and a little bit at acceleration versus time graphs. So we can look at how they relate to each other. We can start with a position and time. We have a velocity in meters per second and time. And I have an acceleration, meters per second squared, and time graph. So those of you that have already done the lab where the two cars come at each other and meet, you know a little bit about how these look. So if I have two cars and they are traveling in opposite directions, perhaps at opposite speeds or different speeds, maybe this one's a little bit faster. I can find where they meet based on where they intersect on a position versus time graph. So if we looked at a blue car and a purple car, they're going to meet right here where they cross. If I wanted to convert this graph and I wanted to display it as a velocity versus time graph, I would do it with one at a time. I would look at my blue line first, and I would say that that is a constant negative slope, which means that I have a constant negative velocity. I'm not changing velocity. Just like we didn't change velocity with the buggies, we're not changing velocity in this graph. The purple one also has a constant slope. It's a little bit slower than the blue one. It covers a little bit less ground in the same amount of time, but it's positive and also constant. So I can draw that right in there. Now we talked about this a little bit. If I was interested in finding out how much ground they had covered, and this was the graph that I had, the easiest way to do that would be to look at the area between the axis and where the curve is that I've just drawn. So the area right here would equal my displacement. So I could do that for the blue one, and I could also do that for the purple one up here. So now we've got our velocity versus time graph. It goes along with my position versus time. If I want to look at acceleration versus time, we really haven't spent much time with acceleration, and we will going forward. But what I should be able to see is that the slopes of these are both 0, and their velocities aren't changing. We know enough about acceleration to know that I'm either speeding up or slowing down. And as I can see here, I'm doing neither. So my acceleration is right on the axis, and it is 0 for both cars. So neither car is accelerating at all. These graphs are going to end up being very important. As a group, they're called a kinematic stack. We're going to use kinematic stacks to make decisions about the movement of different things, whether it's a buggy that's going at a constant velocity, perhaps it'll be a ball rolling down a ramp that's accelerating, or something that was thrown up in the air that is also accelerating in the other direction. But we'll use these a lot this year as we try to graphically represent some of the things that are happening in class. Thank you for watching. I hope this has been helpful.